We've been at some pains, actually, to prove this result of Gauss's law and to see how it comes from Coulomb's law via our fluid analogy. Let's now look at some applications. Let's see how we can apply this law. So applications. Now, it turns out that generally speaking, the only cases where you can really apply this law conveniently, although it's always true, it's a law of physics, the applications are mostly for systems with high symmetry. That's why we stressed the principle of superposition at the very beginning of the lecture. The idea would be you would use superposition in order to, sorry, I just want to get this written out. You'd use superposition in order to decompose a complex situation into component pieces, each of which then may have a lot of symmetry, for which then you could use this powerful new law that we've derived. Now, the specific example we're going to look at is going to be a familiar one to us. I'm going to take our favorite infinite line of charge. So here's my x-axis, and it's all going to be covered with charge. All these little charges in here that will be distributed along that x-axis. And we'll be packing those in with some particular charge density lambda, which will give us the charge per unit length as it has in the past. And our job now is to try to calculate the electric field at some point here. I'll indicate by an open circle above that particular line. So we're asking for the electric field up here like so. Now, for this type of a problem, there's a lot of three-dimensional geometry to picture. So right now, what I've drawn for you right here is a side view. So I'm just going to label it with a little box that this was a side view. I also can consider, and I will over here, an edge view. If you want to look straight down, the edge, or a head-on view of this. And if we look at our wire, in that view, it's just like a dot that we're just seeing as we're looking here directly down this line. Very good. Now, if we're going to apply Gauss's law to a situation like this, there is a general procedure that you can follow, a recipe. And I want to spell this out very explicitly so that you'll be able to apply this in a wide variety of circumstances. And I've found over the years that if I follow my general procedure closely, I can avoid making any of the common errors that I still make after years of doing this. So you shouldn't have any pride involved here. You should always try to go through this very systematically, step by step. So the first step in the general procedure is to get a sense of the general direction of the field. So you're going to use the symmetry that you're given to sketch what the field is going to look like to determine the direction of the electric field. Now, in this particular case, and as I lay out the procedure, we'll do it step by step, but I'll note down here what we're doing as we do it so you can see how this works. So I want to know the direction of the electric field. We've been through this before on the infinite line. If I think of my point up here, everything to the right points up, everything on the left points up and to the right, everything on the right points up and to the left and right components cancel, and I know that the electric field up here is going to be pointing straight up. Now, I need to know the direction of the field, though, not just at one particular point, but I really want an entire field map so I can understand the directions of the electric field. So use symmetry to determine the direction of E and make a field map. Is what you want to try to picture. So I know, it's interesting actually, as I go along this line here, the electric field will all have the same strength because I'm always at equal distances from the wire, and it's always going to be pointing upward. I'm just assuming, because I wasn't told, that the charge is positive. Of course, if the charge were negative, the result would be just that all of the electric field lines point inward, but it's the same general pattern. Now, down below the wire, if I want to make a complete field map, at equal distance, I would have equal length electric fields pointing downward. So this is giving me a general sense of what this electric field looks like, how it's going to behave. If I go to my edge view, it might be a little more illuminating. My question was, what was the field here above the wire? And if I'm below the wire, I've already sketched what happens down there, but we also know that if we go off to the various different sides, we're always going to have a directly outward repulsive force that a small positive test charge would feel from my wire. So this gives you an idea of what that field is going to look like. So I think we understand the directions of the field. The next step is key. In Gauss's law, what we need to do to apply it is to integrate across some kind of a closed surface. That surface is called a Gaussian surface, and we have to pick that surface appropriately. The nice thing, the power of this law is that it applies to any surface. So we have a lot of flexibility, but we want to be sure to pick the surface that is most useful and convenient for us, since we're in control of that particular decision. So what we want to do is we want to pick a Gaussian surface, and Gauss's law, notice as I had stated it, is applies to a closed surface because we want to calculate up all of the flux leaving a particular region of space, so we can use that conservation law that we had in the fluid world to come to our final result. So this Gaussian surface should have certain basic properties. The first thing that it needs to do is that it should pass through the point of interest. In other words, the point at which we are trying to calculate the electric field. It makes sense that this would have to happen. We need to include the point where we're trying to calculate the field. Otherwise, we're not going to gain any information about the field at that particular point. The next thing is going to keep things better for our own convenience. It's that the surface must always be the surface. You have to pick a surface that's always either parallel or perpendicular to the electric field. The reason for that is, again, for our convenience. If we look at Gauss's law, we have this dot product we have to deal with. And if we always pick surfaces that are parallel or perpendicular to E, we'll always have either the cosine of 90 degrees or 0 degrees, whose cosines are respectively 0 and 1. These are simple things, so we don't have to get into a lot of tricky trigonometry. So we want to always be parallel or perpendicular to our surface and pass through our point of interest. So for example, I can kind of see what should happen here, right, at my point of interest. If I want to move perpendicular to my field lines, right, the surface should go this way, at least momentarily as it passes through that surface. That's one direction I could move in. And then that would give me, a kind of part of my surface could go out this way. But a surface is two-dimensional. I need a second direction that passes through my point that's going to be perpendicular to my electric field. And that second direction is a little hard for me to draw here. It would be directly out of the board. So let me try to draw this as sort of a three-dimensional thing, right? So the other direction I can go in is kind of in or out of the board. Now, as I start to come out of the board, you'll notice that as I come out of the board, this helps to look at my edge view, as I'm coming here out of the board, right, the direction of the field is starting to change. And I want to pick a pathway that is always perpendicular or parallel to these field lines. Well, let's try perpendicular. And as I stay perpendicular, you'll see, because these are radial lines, the shape that is always perpendicular to the radial direction is actually a circle. So I can choose then, this direction of my surface is going to sketch out kind of the rib here of a circle. And if I were to continue my surface that way at these various locations, right, I think you can see then that if I'm always staying perpendicular here to my electric field, what I'm beginning to trace out very nicely is some kind of a cylindrical surface. Now, there's more to it yet, because although I have my surface that I've now begun to design as always parallel or perpendicular, the other thing that I have to keep in mind is the surface must contain some charges. If you don't do that, you're going to just end up with 0 equals 0. That's not going to be very handy for us. And the fact that we had to enclose some charges is why I decided to make my surface kind of loop around that wire on the inside. So I'm beginning to enclose that particular surface. And the fourth thing has already been stated, but it's very important, and it's going to come up right now, is, as I had said, it has to be a closed surface. It must be a closed surface. Because this must be a closed surface, I run into just one kind of subtle issue. The surface has to be closed, and if I just took the curved part of the cylinder, it would be an open surface, right? I would have holes here at the top and bottom of my cylinder, and I won't be able to apply Gauss's law. It's always over a closed surface. That was key logic that we used. So to make this a closed surface, I'm going to include then not only the curved part of the cylinder, but I need some caps, right? I'm going to make it a finite cylinder. It's going to include this top face here and this bottom face there, even though the wire continues on towards infinity. So as soon as I've done that, right, as soon as I've chopped my cylinder at the top and the bottom, I'm going to need to define an extra variable, which I better hope is going to cancel out in the final solution, which is going to be the length of my cylinder, L. And I guess as long as I'm defining geometry, I should have said that I wanted to know the strength of the electric field at some distance from the wire, and I will define that distance where I'm seeking the electric field to be r. And then clearly you can see r is going to be the radius of this cylindrical surface. Now, I was forced to include these caps. We have to make sure, however it is that I decide to close my surface, is consistent with my key rule that I'm always parallel or perpendicular to my electric field. And here you can see that the surface does obey that, because the electric field, when I think about this top patch, the electric field is always running parallel to the surface of that patch. Very good. So I've obeyed my rules. The next step then, I've got my surface. The next step is to actually apply Gauss's law. So we are going to write it down, write Gauss's law. And as I've told you before, one key way to organize ourselves is to first just write down the formal mathematical equation that we are using, and then on the next several lines to insert all of the physics that apply to your particular situation, to make sure that you are properly understanding the actual meaning of all of the variables. So when we write down Gauss's law, there's also a particular order that just happens to make things more convenient. You don't have to do it this way, but I find it actually to be very useful in organizing my work. I kind of write it a little bit backwards. I write the enclosed charge part first, and then I set that equal to the closed surface integral across that Gaussian surface I've just picked of the electric field dot dA. So we're going to write that down now. Once we write that down, we are going to substitute and simplify. We're going to write Gauss's law, and then we can simplify the equation a little bit. That always helps, of course, as we've seen before when we write down a formal law and substitute in the corresponding physics. And the last step is the big payoff. If you've done everything right, then in the last step, you should be able to solve for the electric field. So let's try this now. We'll go down below and now write out Gauss's law and begin to apply it to our particular situation. In fact, maybe I'll put it over here on the right. Over here so we can look at our diagram as we are evaluating things. So I want to say here then that the enclosed charge over epsilon naught is equal to integral E dot dA. That's where I've just formally written down Gauss's law. So now, to go to the next step, I have to substitute in the quantities that correspond to my actual situation. Now, in my actual situation, the charges that are enclosed in my surface are not the entire wire, right? It's just that portion, I keep doing that. It's just that portion of the wire which is contained within my surface. In other words, it's this length L of the wire that's all encapsulated within that cylinder. Now, that length of wire does contain a certain charge. The total charge in that wire we should know how to compute because we know the length of the wire L, and we know that lambda tells us charge per unit length. So the total charge in the wire is then lambda times L. Now, our final answer can't depend upon this L, right? The value of the electric field at this point shouldn't depend on this arbitrary surface that I've drawn. So I'm hoping this factor of L is going to cancel out in the final analysis. Next, we come then to the surface integral. To evaluate the surface integral, you have to keep in mind it is a closed surface integral, so I find it very useful to decompose that closed surface integral over the entire can that includes both sides into its different components. It includes the round sides and the top and the bottom. So there's going to be an integral E dot dA on the top surface. So I'm going to call, just to be very explicit, this I will call the top. This here I'll call the bottom. And the round part of the surface I will call the sides. So I've got the one contribution for the integral is over the top. The next one is over the bottom. E dot dA. And then I'm going to have the sides. Now let's think about these three individually. Whenever I do a surface integral, the first thing I'm going to do, of course, is to expand out that dot product. So let's look at this for the top surface. For the top surface, when I look at my dot product, what I'm going to end up with is the magnitude of E times the magnitude of dA times the cosine of some angle theta. Now let's look at that top surface. For the top surface, I know the electric field always points in and along the surface, right? The electric field points this way. dA, what I'm dotting it with, dA for any little patch here of the surface is perpendicular to the surface. dA points outward. So you'll see that dA is always along the line, but the electric field is perpendicular to the line. So in fact, the angle between dA and the electric field will always be a very nice 90 degrees. So theta will equal 90 whenever I'm integrating across the top surface. And the final fact we need to know is that the cosine of 90 degrees is 0. Hence, this entire term will give me just 0. And that's a key step, but it should be fairly intuitive if we think about flow. If you think of this electric field as the flow of a fluid, the fluid is always flowing outward from the line. There is no fluid actually crossing through this top surface. You can go through a very similar argument for the bottom surface, and you will find once again that the dA vector, which points outward, like so, is always going to be perpendicular to the electric field at any point along the surface. So once again, that term will also give us 0. This, by the way, is the reason for the rule that your surface should always be parallel or perpendicular to the electric field. Very good. So now I'm down to just one term, which is this term having to do with the integral around the sides. So let's analyze that one out in a little more detail. I'll write it a little bigger. We've got a little more room here now. So that's integral around the sides. My rule, again, is to always evaluate that dot product first. So that dot product would give me the magnitude of the electric field along the sides, around that curved part of the surface, times the magnitude of the area vector, times the cosine of some angle theta. Now in this case, when I'm talking about the sides, notice that if I think of a little area patch somewhere, maybe up here on the top, in that case, the electric field is straight up, but also the dA vector is straight up. The angle between these, and the way we always measure the angle between two vectors is we draw them tail to tail. If I draw that particular angle, right, here's the electric field pointing straight up. dA is pointing in the same direction. I'll make it just slightly different looking direction for the purpose of a sketch. We want this angle that exists between these two vectors. That angle then is clearly 0. And in fact, as you go across the entire, as you go across the entire surface, at any location, if I look at any patch, the outward vector will be both the dA vector, will be perpendicular to that surface, will be exactly lined up again with the electric field vector. So dA and E. You can also see that maybe more clearly in the edge view, right? In the edge view, all these vectors here are the dA vectors, and they are also the exact same direction as the electric field. So my angle then is always 0, and this is nice because the cosine of 0 is a very simple number. That cosine is just 1. So I'm getting there now. The next thing I want to think about is these magnitudes. The magnitude of dA vector is just the area element dA. It's the area of each patch as a scalar. The magnitude of the electric field at all these points along these sides, these curved sides, the curved side, maybe I should have just called it side, but the curved side, right, the electric field there, its magnitude is always the same because every point along this side, or here in my edge view, every point along this side is at the same distance r from the center because I chose to use a circle. So that electric field is constant, and the magnitude of it, it just tells me the electric field at distance r from my wire. So we're getting now to the home stretch. Now that we've substituted everything in there, it's time to continue with these simplifications. Because this E is a constant everywhere around the side, because the sides are at constant distance r from the center, that electric field E can be pulled out of the integral, and that leaves me then with the electric field at distance r, that is the thing which I seek, times the integral of dA, which just means to add up all of the area patches on that side, that curved side. So this gives me just the total area. So now I need to know the area of the curved side of a cylinder. And you might recall that the way to remember that is to look at the perimeter here of the cylinder, right? And you can imagine cutting the cylinder, say, along this top surface and flattening that cylinder out, unraveling it and flattening it. And then what you'll find is the cylinder was made from a rectangular piece of paper, for instance, which had length L, if we want to imagine as a piece of paper, and the width of it, when I unravel it, will be this circumference, and the circumference of a circle is 2 pi r. So that area will be the length times the width of that paper when I unravel it, which would be L times 2 pi r. So my final result then gives me the electric field times 2 pi r L. Oh, I'm excited because look, there's an L here. And this side of my equation, when I track it back up, was supposed to equal lambda L over epsilon naught. And so you can see then that the L's, just like I was fantasizing about, the L's are going to cancel out. And in fact, now I'm ready for step 4. I can just solve this for the electric field. So the final result then will be that the electric field at distance r will be, and when I look at this equation, I can solve it by dividing both sides by 2 pi r. That will just leave me E on this side, and put 2 pi r in my denominator. So my final answer will be lambda over 2 pi epsilon naught r. That is just giving me the magnitude of the electric field. If I want to make this into a proper vector equation, I need to have directions for my electric field. This gives me the magnitude, and the direction we know is just radially outward from the center of the wire. I could put an r hat there and put a box around that. That's a nice, clean result for my cylinder. Whew. Now, here's the last fun part. I'd like to check this. I'd like to check if this matches up with the answer that we've had before from doing, remember we did this in the previous lecture with this very difficult integral. Let me just recall for you the result we had previously. What we had found for the electric field via our integration was that we had twice Coulomb's constant times lambda divided by the distance. In the previous lecture it was called z, but that was just the distance above the line, so that's divided by r. And that was the magnitude that we had gotten. And of course we would conclude also in that case that the direction of the electric field was upward when we were above the line, but in general it's always outward from the center of the line. So it's always in this r hat direction. So do these two things line up? Well, there's only one way here to find out. We have to substitute in what we know Coulomb's constant to be. Now Coulomb's constant, we had solved for that in terms of our epsilon naught, which is really our more preferred way of going. Once you get used to Gauss's law, you see that epsilon naught comes up quite a bit. Here's our definition, right? It's 1 over 4 pi times Coulomb's constant. Equivalently, Coulomb's constant is 1 over 4 pi times epsilon naught. So let's substitute in then 1 over 4 pi epsilon naught for Coulomb's constant. And when I do that, what I will have is, in the numerator, I'll have my lambda. I've got numerator and denominator, and the unit vector, of course, is always r hat. In the numerator, there's my lambda. I'm substituting for kc. There's a 2 in the numerator, but Coulomb's constant is going to give me 1 over 4 pi epsilon naught in the denominator. So the 2 in the numerator and the 4 in the denominator give me just a 2 in the denominator. And what's left over is then the pi times the epsilon naught. So I'll get 2 pi, holy moly, look at that, 2 pi epsilon naught r. Look, beautiful. It's exactly what we got from doing that whole nasty integral with all of those vectors. So I hope you can see that this Gauss's law really works out very nicely. It takes a bit of practice, but you can see it's much less tedious and grungy than going the route of doing the integrals. So I'm very excited that I actually got this to work out properly without any bugs this time. So once again, happy professor symbol, and that will end today's lecture.